Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of medical horse data. It's called horse colic dataset. Colic is abdominal pain in horses. But the point here is we have this outcome variable all the way at the end that basically we're trying to predict if a horse will survive or not based on a series of medical features. Alright, so we're just going to hop into the notebook and I'm going to use a decision tree classifier and a random forest classifier to make our predictions. Random forest is just a bunch of decision trees trained on subsets of the data and averaged together, so as a form of ensemble model. So we're going to try with just a decision tree and then see how the ensemble version compares in accuracy. So I'm going to import NumPy and pandas just to work with the data, and then the standard scalar and train test split function from sklearn for preprocessing. So I'm going to go ahead and import those and then load the data in using pandas.readcsv. And we can get the CSV file path right over here, and copy that, paste it in, and we'll take a look. And right away, first thing we can notice about this data set is that we have some missing values here. And I mean, so I guess we should just get a little information with data.info. And you can see we definitely have some amount of missing values in many of the columns. There are 299 total rows, so not a lot of data, but definitely enough. And you can see like some of these have quite a few missing values. It's only 53 non-null in the dataset. Also, we have a lot of object columns, so we're going to have to do some serious encoding. Okay, so let's start preprocessing. And what I'm going to do is create this function called preprocess_inputs that's going to take in a data frame. In this case, it will be this data frame that we pass in. We're going to start by making a copy of it, just so that we can modify a fresh copy. And at the end, we're going to return x and y, where x, y is what is the column we're trying to predict. So df sub the, if we actually look over here, there's this outcome column. This is what we're trying to predict. Either the horse lived, died, or was euthanized. And so we're just going to grab the outcome column and store it in y, and we'll make a copy of that as well. Then x is going to be everything except the outcome column. So I'm going to drop outcome from df, and I'll make a copy of that as well. Then we'll return x and y. So currently all this does is split df into x and y. So if we run preprocess inputs on our data and store it in x and y, then x looks like this with 27 columns. Originally we had 28, but we dropped the one outcome column, and y should be just the outcome column. So now we're just going to keep adding things to the preprocess inputs function and keep checking how it affects x and y. So I think we might want to check what kind of data we're dealing with before we deal with the missing values, because it seems like there's a lot of categorical features here, features that are non-numeric, right, that have text labels, and we want to see which of them are going to be one-hot encoded. So the reason I'm saying this is because one-hot encoding automatically deals with missing values, so we don't have to fill them in any way. So before we just go ahead and fill everything, we can one-hot encode first. So let's sort of categorize all of our features into three buckets. We have binary features that take only 2 values. We'll store them in a list. We have ordinal features that take on an ordering of values. And we have nominal features. I should say this obviously has more than 2 values, otherwise it would go in binary features. And a nominal feature is a feature that has more than 2 values but has no inherent ordering. So how do we know what to put in what? Well, in the x, we can type x.select dtypes and pass in object to get only what's going on? No attribute. Oh, select dtypes. Select dtypes, pass in object, and we'll get only the columns that have object data. So essentially only string data here. So with this, we can actually get, well, notice if we type .columns, we can just get the names of those columns that have object data. And then we can iterate through these columns and return a dictionary that maps a column name to a list of the unique values in the column. So it'll be x sub column dot unique turned into a list, and this column will be every column in the columns listed below, which is just the categorical columns. So that's a dictionary that maps a column name to a list of the unique values in that column for every categorical column. So if we run that, we can now see the kinds of values that are in each column. And now we're going to ignore anytime we see NaN. That just means it's a missing value, and we're going to deal with that later. So ignoring the NaNs, we're going to look at what kinds of information we have. So surgery, this is a binary feature, right? Because there's only two values. It doesn't matter if there's an order or not. We'll just encode one of the values as 1 and the other value as 0. So I'm going to put surgery up here in binary features. Okay, then age is also binary, right? Because there's only two values. So I'm just going to put that in there as well. Temperature of extremities. You can see there is actually an ordering between these values. We go cold, cool, normal, warm. So this will be put in ordinal features. And okay, so peripheral pulse. This is also ordinal. You can see absent, reduced, normal, increased is the order. So we'll put peripheral pulse in ordinal as well. Okay, then mucous membrane. This is nominal. There's more than two values and there's no ordering between them. So this is going to go over here. And I'm just going to continue this process all the way down. I don't want to take too much time doing it, so I'm just going to paste in the correct values that I got them before. So we have 4 binary features. We have, I believe it's quite a few ordinal features. 1, 2, 3, 4, 5, 6, 7, 8, 9 ordinal features. And for nominal, we have just 3. So most of our features are ordinal. And this is a full list of all of the values here. Notice that I'm only doing this in X. We still haven't touched our Y, which is the outcome, if the horse lived or died or not. But now with these 3 categories, we can encode each set of columns separately with a different encoding scheme. So let's create 3 different encoding methods. We're going to have a binary encode function, an ordinal encode function, and a nominal encode function, also called one-hot encode. So, alright, for each one, we're going to pass in a data frame and a list of columns. We're going to start off each one by creating a copy of our data frame. And in the end, we're going to return the data frame after transformations have been applied. Now the type of transformation is going to depend on the encoding scheme. So for binary encode, we want to pass in, we want to specify which of the 2 values is going to be assigned to 1 and which is going to be assigned to 0. So we are going to specify a list of positive values, which will match up to the columns. And so for example, we'll have one for surgery, where the 2 values are no or yes. So we'll say yes is the positive value. Yes is going to be encoded as 1. So we'll pass in yes as the positive value to this function. Now we're going to pass in a bunch at one time, so I'm going to iterate through for column positive value in, and I want to iterate through it simultaneously, so I'm going to zip them together. Zip columns positive values. And zip, if you don't know, is this amazing function that takes 2 lists. I'm just going to make 1, 1, 2, 3, and another A, B, C. And if we zip them, and we can view it as a list after that, it will pair up element-wise 1 and A, 2 and B, 3 and C into tuples, so that we can iterate through 2 at a time like this. So we can get the column and the positive value that go together. So we're going to do, alright, so for each pair of column and positive value, we're going to take just the column and apply a lambda function to it. So this is an anonymous function that takes as input x. X will be a given value in the column, and x will become 1 if x is a positive value, and otherwise it will become 0. So this is the encoding. X either becomes 1 or 0 depending on if it's the positive value or not. So there we go. That's it for binary encode. For ordinal encode, we have a very similar thing. I'm just going to grab this, except instead of positive values, we're going to pass in some orderings. And this is going to be, a given ordering will be a list of all the unique values in an ordinal feature. So for example, this one, not counting NaN, like I said, but we have to make sure it's in the right order. So an ordering will be cold, cool, normal, warm. And that way we can index the list, so we get 0, 1, 2, 3, once it's in the right order, and that will be our encoding. We'll just encode the ordering into unique integers in ascending order. So we'll pass in orderings to our zip. We'll zip together the columns and the orderings, and then iterate column ordering 2 at a time. So now we're working with a column and an ordering, and we're going to just basically do what we did up here, except instead of this lambda function, we'll have a different one that instead of doing 1 or 0 depending on if it's a positive value, we'll just change x into ordering.index of x. So we'll pass x into the ordering and check where in the ordering it comes up, and then index in that location to get an integer, and then set x, which was originally a unique value. Originally a value in the column is now an integer. And so this is going to do it for us, ordinal encode, our feature. Now for one-hot encode, we're going to do something similar here, except instead of orderings this time, we're going to pass in some prefixes, and I'll explain what that does in just a moment. But we're going to iterate column prefix for we're going to iterate through column prefix pairs in zip of columns and prefixes. Oh, sorry, this is not be a C there. Okay, and this no indent. Okay, so let me show you what this function pandas.getDummies does. If we pass in a data frame, just a certain column, we're going to use a nominal feature here, mucous membrane. If we're just taking a look at the mucous membrane, first of all, let's just look. Let's make it x. Let's just look at this. It is a you can look at the unique values in it. It's a nominal feature that takes on a bunch of different values, right? But there's no ordering between them. If we get the dummies for this column, which is what this getDummies function does, it takes each unique value, gives it its own column, and there will be a 1 for a given example in the column that the original value came from. So you'll see the example 1, we have pale cyanotic. So for 1, we have a 1 here in pale cyanotic column and zeros in all the others, right? Now note that this already takes care of missing values, like I said. If it's an NaN or missing value, we just have all zeros straight across, and that will just completely take care of it for us. Now if we wanted, we could fill these in with a mode and then encode it properly, but I feel like, I don't know, this might be better. I'm not sure the effects. I might want to test that at some point though. Okay, so now that we have these dummies, I want to just also note that we can include a prefix. Let's call it mucus. That will just put mucus at the beginning of each column name so that we know where these columns are coming from. And so now down here we're going to pass in a list of prefixes along with a list of columns, zip them together, and then iterate 2 at a time, column prefix. And we're going to create a dummies for each column. For each column and prefix, we'll create a dummies data frame with pandas.getDummies, pass in df subcolumn, and we're going to include the prefix that we pass in. So now with these dummies, what we're going to do is take the original data frame and concatenate using pandas.concat the data frame itself along with the new dummies side by side. So we're just pasting it onto the right side of the data frame. And then when we're done, we can just drop the original column from which we created the the dummies in the first place. And that's it. These are our 3 encoding schemes. So let's run that. And then down here, we're about ready to encode. We just have to specify the positive values, the orderings, and the prefixes. So I don't want to take too much time doing that, so I'm just going to paste it in, and I'll explain. These are the positive values for each binary feature. Surgery, the positive value is yes. Age, the positive value is adult. Surgical lesion is yes. CP data is yes. If you look down here, right here, you can see we just chose these sort of arbitrarily. We could have used no as the positive value, but I think yes makes more sense. And down here as well. So now we're going to get the orderings for our ordinal features. I'll paste those in as well. These I went through and ordered them out. All the unique values in a given ordinal column, I ordered them from cold to warm, from absent to increased, from less than 3 seconds to more than 3 seconds. You can see I did for each one. And there's for example, this pain column has slight, moderate, severe, or actually no, this one, mild pain, severe pain, extreme pain. I looked at there's another file here that gives some more information about the horses, about the columns, so that we know extreme pain comes after severe pain. If you're ever in a situation where you're not sure of the ordering that should be used, it's probably best to use a one-hot encoding instead. For our nominal features, we're going to need some prefixes, and we can just make these up on the spot. These are nothing. There's only 3 of them anyway. For mucous membrane, let's have MM. For abdomen, we'll have AB, and for abdomo appearance, we'll have AA. Okay, so now we're ready. We have our binary features and positive values, our ordinal features and orderings, and our nominal features and prefixes. Now we're going to just run 3 lines of code. Okay, actually, before we actually encode them, remember I was talking about the missing values in this data. The reason I didn't fill the missing values yet is because we were looking for which ones are nominal, because nominal, the encoding will already take care of it for us. So now it's time to deal with the missing values. So I have sort of 3 different encoding schemes I want. We can take a look at the missing values by typing x.isNA, which will give true in a given location if there's an actual missing value in that spot. So you can see we have a missing value here, so we have true down here. If we sum this over the rows, then we'll get the total number of missing values in each column. And you can see there's quite a few, and in fact there are missing values in both numerical columns and in ordinal columns and in nominal columns. So we need 3 different ways to fill. So what I'm going to do is for every column, so for column in df.columns, we're going to check if it's an object column. So if column is in df.select dtypes object.columns, so essentially if we're dealing with an object column, then we're going to check if it's a nominal feature. Then we check if column, actually if it's not in nominal features, then we know it's going to be an ordinal feature or a binary feature, in which case we're going to use the same encoding scheme, which is filling with the mode. So you can, for a numerical feature, you can use a mean to fill, right? You can calculate the mean and then fill in the missing values with the mean. But for categorical features, you can't get a mean. You can get a mode though, which is the most frequent occurrence. So we're going to say df subcolumn dot fill NA, which will fill all the missing values with a given value, and the value we're going to give it is df subcolumn dot mode, and we actually have to include sub-0 at the end. The reason for that is if you want to grab one of these, temperature of extremities, if we get the mode, it comes back as a pandas series, and if we just want the string value, we got to do sub-0 to get the actual string value. Okay, so we're filling in the missing values in a column, in a ordinal feature with the mode. So let's actually set that to be the column. And then we're going to jump back 2 spaces. We don't care about the case where we're dealing with a nominal feature, because that is already taken care of by the one-hot encoding. But else, for this if statement, right, so if it's not an object column, meaning if it's a numeric column, then we're just going to do the same thing, but use the mean, because for numeric, we can use the mean. Alright, and we don't actually have to include the sub-0 for doing mean. Okay. So now our missing value should be filled. If we run this and take a look, we should only have missing values in the nominal columns. So x.isNA, we'll check it again, sum across the rows. So all 3 of these that have missing values remaining should be nominal. Mucous membrane, abdomen, and abdominal appearance, which actually happen to be all 3 of our nominal features. Alright, so now we can encode. So first we'll do binary encoding. df equals binary encode. That's the function we wrote before, right? We're going to pass in the data frame itself, pass in a list of columns, which will be the binary features, and a list of positive values, which will be the positive values that we specified. Then, ordinal encoding. So ordinal encode. The columns here are going to be the ordinal features, and we don't have positive values, instead we have orderings, which are going to be given by orderings that we specify here. Then last, we have one-hot encoding on the nominal features, so make this nominal. And orderings we're not using, but we're going to have prefixes instead. Prefixes equals these prefixes. Alright, so let's run this, this. And you should see we now have 38 columns from these new one-hot columns at the end. But what you'll notice is that the whole data set is in numeric form, and that means it's ready to be fed into the model. There's a few more steps we have to do. I believe just 2 more. One is to deal with the y, which is still not encoded properly. For this, it's much easier to encode. If you're just going to do one column and you know what each value wants to be mapped to. Here, I should probably mark this down. Let's categorize categorical features. And then down here, fill missing values. Down here, encode categorical features, feature columns. And now we're on to encode labels. So here's our labels. We can check all the possible values. In fact, let's get value counts to see how many of each. So it's either lived, died, or euthanized. So what we can do, lived will be 0, 1 will be, died will be 1, and euthanized will be 2. This really doesn't matter so much. With this kind of encoding, it really doesn't matter what you make it. But we can create a label mapping that's going to map lived to 0, died to 1, and euthanized to 2. Right? And then all we have to do, if we have a dictionary that maps key value pairs like this, we can just say df sub outcome, that's our label column, dot replace label mapping. We can just pass in the dictionary and it will apply the mapping on its own. So we'll make that the new outcome column. And if we check this now, our y now is no longer lived, died, and euthanized. It's now 0, 1, and 2. So the last thing to do after all this, at the very end, after we split, we want to scale x with a standard scaler. So right now, every column in x takes on a very different range of values. Over here it goes up to 85, over here it goes up to 11,000, and then over here it just goes 1, 2, maybe 3, and then over here we know it's just 1 and 0. So these very different ranges of values. It's a lot nicer for the model if we pass in oh, I also just noticed hospital number. This is not a useful feature. Sorry, let's actually check. Okay, x sub hospital number. And just take a second to check this. Let's get the number of unique values. So the length of uniques. Okay, so you can see we have some, very few of them are the same. 283 unique values in the hospital number. So it's a good question. In its current state, this is not encoded properly, because right now it's being treated as an ordinal feature, as a continuous range feature. But the problem is these are not continuous ranges. This is not larger than this, right? It's not a measure of how good a hospital is. These are all independent of each other. So this is actually a nominal feature, even though it's encoded as numbers. What we should do is one-hot encode this if we want to keep it on. So it's sort of hard to make the call. There is some useful information in here, there's no doubt, because there's some of them are repeated. So if, for example, like one hospital is really good at saving horses, this should pick it up. So I think we should encode it. So luckily we have this function. It's very easy to do that. So where is it? It's all the way at the top, right after age. So right here in nominal features, I'm just putting in hospital number, and I have to give it a prefix as well. So HN for hospital number. Alright, and then all we have to do is run. Oh, what's this? Did I not put a comma? Usually this means I forgot a comma. Oh yes, no comma. Okay. Alright, so now we run X. We now have 320 columns, so we added a whole bunch of different hospital number features. Right here, you can see each different hospital number has its own column now. And I don't know how this will affect the performance of the model, but either we one-hot encode it or we drop it. There's no point in keeping it on in its original state. Okay, so let's see. Oh yeah. Alright. I think we can scale now. So standard scaler, like I was saying before, each one of these features takes on a very different range of values, and it's a lot easier on the model if they take on the same range of values. So that's what a scaler does. We'll use the standard scaler from sklearn, and this will give each column a mean of 0 and a variance of 1, so that most of the values in each column will take on a range of -1 to 1, and their means will be at 0. So to make the transformation, it's very easy. You just call scalar.fitTransform, which will fit and transform the scalar in one go. You could also call fit and transform separately if you wanted to, but we're going to pass in x. And we'll store in x again when we're done. So this actually returns a NumPy array, and I want to turn it back into a data frame, pandas data frame, just so that we can view it nicely. And we'll keep the column names as they were before. Alright, so now we run x. Currently, before you can see everything takes on different ranges of values. Now everything takes on the same range of values. Almost, yeah, every column has this range between, there's no hard limit, but most of them are pressed down between -1 and 1. Okay, and they have mean 0 as well. Alright, so what to do now. I think we're ready. I think we're ready to train. We have our X, we have our Y, we're good to go. So for training, let's split the data into a train and test set. So we have X train, X test, Y train, Y test. So this is, we're going to split X into X train and X test, and we're going to split Y into Y train and Y test using the train test split function from sklearn. And we're passing in X and Y, and then we're going to specify a train size. So how much of the data do we want to put in the train set? And 70% is standard. I will do 70%. And I'll include a random state as well. This is just a number that allows us to reproduce the results. This function also shuffles the data, so it's good to shuffle it the same way every time we run this code. Alright, so we run that. We now have 4 different sets of data that we're going to train and test on. So I said earlier we're going to use a decision tree classifier and a random forest classifier. So first let's create our regular model, which will be the decision tree classifier. And we're going to fit the model, so model.fit, on the train set only. So X train, Y train. Alright, and then when we're done, we'll print out the result, decision tree accuracy. And we're going to format it as a number to 2 decimal places with a percent sign after, and we're going to type .format and pass in model.score. So this function will test the model after it's been fit on a test set. We pass in X test, Y test. So it'll make predictions on X test, then compare them to Y test and return the percent accuracy. Actually in decimal form, so let's multiply by 100. And we end up with an accuracy of 62% on our test set. So looking at other notebooks, this seems to be about on par with what other people are getting. It doesn't seem like people are getting very high accuracy with this data set. That's probably because there's very little data, and there's not necessarily good enough information in the set to accurately predict the outcome. So 60 is fairly good. It's about average, I think. So let's see if we can get a better result using a random forest classifier. So this is an ensemble model, and usually ensemble models are more consistent and higher performance than regular single models, but it really depends on the task. So this is going to be a random forest classifier, and we're just going to do the same thing here, ensemble model.fit on the train set, and we'll print out, I'll just copy this, we'll print out the accuracy, except this will be random forest accuracy, and we're going to score with the ensemble model instead. Alright, and we have quite a performance boost. We're up to 73.3% now, and that's actually higher than any I was able to find in the other notebooks. So it seems like we got a huge performance boost by using an ensemble model in the setting. Alright, so that will sum up today's video. Thank you so much for watching. I hope you enjoyed the video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.